In October of 1975, the United States Army switched on a nuclear missile whose entire job was to detonate close enough to hurt the people it was defending. That is not an exaggeration, and it is not enemy propaganda. It is the plain operating description of a missile called Sprint, and the reason the Army built it anyway comes down to a single number: 10 seconds. Hold on to that number, because it is smaller than almost anything else in this story, and it is the reason the whole program is shaped the way it is. The warhead on Sprint was called the W-66. It weighed about 150 pounds, measured 18 inches across and 35 inches long, and its yield was about 2 kilotons, roughly 1/7 the size of the 15-kiloton bomb dropped on Hiroshima. It killed by a burst of neutron radiation, not by heat or blast. Sprint itself did nothing to Mach 10 in about 5 seconds, pulling roughly 100 G on the way there. This was not a weapon built by people who had stopped caring what it might do to the ground underneath it. It was built by people who had run into one very narrow, very specific problem, and 10 seconds is the exact width of the gap they were trying to close. If a Cold War program that sounds too reckless to be real is your thing, stick with this one, because the reason for that 10-second number has a name inside the missile defense world: nuclear fratricide. And once you understand it, the weapon that sounds like the Army's most dangerous idea turns out to be closer to its most careful one. To see how something this strange became official policy, you have to go back almost 20 years before Sprint left a drawing board. In the 1950s, the Army handed Bell Laboratories and its manufacturing arm, Western Electric, a contract to design a system that could shoot down an incoming intercontinental missile before it reached American soil. That program was Nike Zeus, a single large interceptor built with help from Douglas aircraft, meant to destroy an enemy warhead far out in space using the raw power of its own detonation. Nike Zeus never satisfied the Pentagon, so by 1963, it had grown into a broader program called Nike-X. Nike-X added a second radar, the Missile Site Radar, built by Bell Labs with Raytheon, and it split the intercept job into 2 separate missiles instead of 1. The long-range half evolved directly out of the old Zeus interceptor and was renamed Spartan. The short-range half, built for the final seconds before impact, was Sprint. On March 18, 1963, Martin Marietta of Bethesda, Maryland, got the contract to actually build it. In the fall of 1967, Defense Secretary Robert McNamara announced these pieces: the radars, Spartan, and Sprint would finally deploy under a new name, Sentinel. He was careful to call it a light system on purpose, and the reasoning behind that word is its own overlooked part of this story. China had detonated its first hydrogen bomb earlier that year, and Sentinel's stated mission was defending American cities against a limited Chinese attack, not the far larger Soviet arsenal. McNamara had already argued privately and in public that a full, heavy shield against the Soviets specifically would backfire. His own estimates put the cost of defending against a Soviet missile at roughly 20 times the cost of building one, which meant a heavy American shield would simply push Moscow to build more missiles until the defense was overwhelmed again. An arms race with no stable endpoint. A light, deliberately limited system aimed at China was, to McNamara, the version that did not make the larger nuclear standoff worse. That plan lasted about a year and a half, and it did not die in the Pentagon. It died in a high school gym in Reading, Massachusetts. On January 29, 1969, in the middle of a blizzard, more than 1,000 people showed up at Reading High School to confront the Army Corps of Engineers over a proposed Sentinel site nearby, at a place called Sharpner's Pond. Residents had been told the installation's radar could pose a radiation hazard to homes and schools within its beam. 2 days later, Senator Edward Kennedy sent a letter to Defense Secretary Melvin Laird, laying out the opposition's case, and the fight jumped straight from a town meeting into a congressional one. On February 6th, Laird agreed to review the entire program and halted construction at Sharpner's Pond. The site was canceled outright within the year, and cities across the country, Chicago's suburbs among them, were raising the identical objection before Sentinel had built almost anything. 2 years after that gym in Reading, under President Nixon, the whole program was renamed again to Safeguard, and its mission was quietly reversed. Instead of ringing cities, Safeguard would ring missile silos out on the empty plains of North Dakota, protecting weapons instead of people, precisely because nobody wanted a nuclear interceptor's blast radius anywhere near a school again. The program people vaguely remember as a city shield never actually defended a single city. A blizzard, a letter, and a senator are the reason it defended Minuteman silos instead. Even that reversal did not guarantee survival. In August of 1969, the Senate took up an amendment to cut off all further Safeguard funding outright. The roll call ended in a 50-50 tie, broken against the amendment by Vice President Spiro Agnew. A separate amendment from Senators John Sherman Cooper and Philip Hart, aimed at blocking deployment while research continued, failed by almost as thin a margin, 51-49. The program that would eventually stand watch over Minuteman silos in North Dakota came within a single vote of never being funded at all. And while all of this played out in American town halls and committee rooms, the Soviet Union was solving the identical technical problem in total isolation, with none of the public debate. Around Moscow, the Soviets built a system called A-35, operational from 1972, with its 64 launchers spread across 8 sites, defended by an interceptor called the A-350, carrying a warhead in the 2 to 3 megaton range and capable of roughly Mach 4. Nixon signed the ABM Treaty in Moscow in May of 1972, across the table from Leonid Brezhnev, in the same summit that produced the broader SALT agreement, and it allowed each side exactly one deployed system, capped at 100 launchers and 100 missiles. The Soviets built theirs to ring a capital. The Americans, after reading, were no longer politically able to build theirs anywhere near one. 2 rival superpowers, with no access to each other's engineering, still arrived at the same forced conclusion. With the guidance technology available in the 1960s and 70s, the only reliable way to kill an incoming nuclear warhead was with a nuclear warhead of your own. That convergence is not a coincidence you can wave away. It is the answer physics kept handing back to anyone who tried to solve the problem honestly. And solving it honestly meant running straight into a second problem hiding inside the first one. A problem that only shows up once you are actually using nuclear weapons to intercept other nuclear weapons in sequence. That second problem is nuclear fratricide, and it earns its full definition here because the phrase does real work once you understand it. Fratricide happens when the detonation of one nuclear warhead, fired to destroy an incoming missile, disables a second interceptor launched shortly afterward. It can happen through blast pressure, through the electromagnetic pulse of the first explosion frying the guidance electronics of the next missile, or through a spreading cloud of radioactive debris that blinds the radar, tracking the second target. Analysis of the problem, including work by economist Alwyn Young archived at the London School of Economics, puts the safe spacing at roughly 10 seconds to avoid the fireball effect outright, and either under a minute or over an hour to avoid the slower debris cloud effect instead. 10 seconds. Under a minute or over an hour. Nothing in between is safe. That is an extraordinarily narrow set of acceptable windows for a system with, at most, a few minutes total to detect, track, and kill an incoming warhead. That math stopped being theoretical fairly quickly. Sprint began flight testing at White Sands Missile Range in November of 1965, and by the time that campaign wound down in August of 1970, it had flown 42 times. Testing then moved to the Kwajalein Atoll in the Pacific, where the system was tried against real targets flown in across an ocean, a proving ground that ran from 1970 through 1973. 3 years and half a world away from the North Dakota site, the missile was actually built to defend. On March 17, 1971, 2 Sprints carrying the test designations FLA-49 and FLA-50 launched together from Mech Island in a salvo, exactly the paired shot the 10-second rule exists to govern. Their target was a genuine Minuteman I re-entry vehicle, launched 4,800 miles away at Vandenberg Air Force Base in California. Both interceptors found it. The warhead was destroyed. One documented series from that broader campaign broke down as 12 successes, 2 partial successes, and 2 failures, a normal, unglamorous ratio for a missile trying to do something nobody had ever done before. By the time Sprint's Kwajalein series ended, 29 of its shots there had succeeded. The 10-second window was not a number on a blackboard by then. It was a spacing rule that 2 live nuclear-capable interceptors had already flown under, together, on the same afternoon, without erasing either one from the sky. This is exactly why Safeguard split the job into 2 completely different weapons instead of one bigger interceptor. Spartan fired first, as far out in space as possible, its much larger warhead's kill radius wide enough that it did not need pinpoint accuracy against a fast target that might be surrounded by decoys. But if Spartan missed, there was no 10 seconds to spare for a second Spartan without risking fratricide against the first detonation, and the incoming warhead was still coming. Sprint had to be small, fast, and close range, and its own warhead had to avoid creating a second fratricide problem at low altitude near the ground it was defending. That is the whole reason the W-66 exists in the shape it does. It was an enhanced radiation warhead, the first weapon of its kind fielded anywhere in the world, meaning most of its destructive output was tuned toward a short, intense burst of neutron radiation rather than heat or blast pressure. A conventional nuclear weapon of the same size would have thrown a far bigger fireball and a far bigger debris cloud, exactly the 2 things the 10-second rule exists to avoid. The W-66 traded blast for radiation on purpose, because radiation could disable an incoming warhead's electronics and fissile material without recreating the fratricide problem Sprint was built to get around. 18 inches across, 35 inches long, 150 pounds. Built small on purpose, against a decision window measured in single digits. Delivering that warhead in time made Sprint one of the most physically extreme machines the Army ever fielded. The missile itself was small by ICBM standards, 26.9 feet long, 53 inches across, weighing about 7,700 pounds, with a reach of only about 25 miles and a flight ceiling near 19 miles. Compared to Spartan's reach out into space, that range sounds almost modest, and it was supposed to. Sprint was never meant to cover distance. It was meant to cover the last few seconds. It did not simply ignite and climb out of its underground silo the way most missiles do. It was ejected first, mortar style, blown clear of the launch tube by a separate charge, so the airframe was already moving before its own rocket motor ever lit, because igniting that much thrust while still inside the tube would have destroyed the launcher itself. Once clear, it accelerated at roughly 100 G, reaching Mach 10, over 7,600 miles per hour, in about 5 seconds. At that speed, low in the atmosphere, friction heated Sprint's skin past 6,200 degrees Fahrenheit, hot enough to ionize the surrounding air into a glowing plasma sheath, a layer of charged gas that would have blocked an ordinary radio guidance signal completely. Sprint carried no seeker of its own. It flew on radio command guidance, steered by signals sent up from the ground every fraction of a second, which meant a blocked signal was not an inconvenience. It was the difference between a hit and a clean miss. A conventional radar dish has to physically rotate to find a new target. Far too slow for anything closing at Mach 10. Engineers answered that with a phased array radar instead, a system that steers its beam electronically rather than by moving a dish, retargeting in a fraction of a second. And Bell Labs built one with enough raw transmitted power to push a guidance signal through Sprint's own ionized exhaust. The tiny warhead. The impossible acceleration. The radar built to talk to a missile wrapped in its own ionized exhaust. Every part of Sprint points the same direction. This was the constrained option, not the reckless one, built around a 10-second problem that left no room for anything bigger, slower, or simpler. Which raises the obvious question. If the design was this careful, why does Sprint get remembered? On the rare occasion it gets remembered at all, as a symbol of Cold War madness instead of the opposite. Part of the answer is that almost nobody ever saw how the system was actually meant to be used. A Minuteman class BM crosses the pole from launch to impact in about 30 minutes. Safeguard's real defense sequence started with the Perimeter Acquisition Radar, a General Electric installation 120 feet tall, built with 17 million pounds of reinforcing steel and 58,000 cubic yards of concrete, and hardened against a nearby nuclear blast that scanned north for the first sign of an attack and could pick out something the size of a basketball at up to 2,000 miles. That data fed the missile site radar, the system Bell Labs and Raytheon built together, which tracked individual objects, sorted real warheads from decoys, and directed the actual intercepts. Out of a 30-minute flight, the entire engagement, both shots, happened in the last handful of minutes, and the 10-second spacing rule governed the tightest part of that window. Spartan launched first, using its wide kill radius to cover for uncertainty at long range. Sprint's entire reason for existing was to be the layer that fired only if Spartan missed. Every single Sprint launch, by definition, meant the primary defense had already failed, and an armed nuclear warhead was seconds from an American target, almost certainly the Minuteman silos near Grand Forks Air Force Base that the whole Michelson complex existed to protect. The site reached full operational capability on October 1, 1975, with 30 Spartan interceptors and 70 Sprints in the ground, right at the treaty's 100 missile ceiling. And it had cost about $6 billion to build, something like $35.9 billion today. This is where the most common misreading of Sprint takes root. People who have heard of the missile, even people who take Cold War hardware seriously, often treat its existence as proof that detonating a nuclear weapon over American territory was somehow the plan, the default, the intended outcome. That reading has the doctrine exactly backwards. The claim that Sprint was built to detonate close enough to the ground to matter is technically true. What that framing leaves out is that every single time it happened, the alternative was a live nuclear warhead reaching the exact same place, completely untouched. Sprint sat as far down the decision tree as engineers could push it, specifically because everyone involved understood it was the option nobody wanted to reach. And this is where the 10-second window stops being a science lesson and becomes the entire logic of the doctrine. The reason Safeguard needed two completely different weapons instead of one larger interceptor was that single number. A single design could not be both far-reaching enough to intercept early and small enough to fire safely, seconds later, without risking its own radar coverage or its own follow-up shot. Splitting the job in two and accepting the terrifying-sounding cost of a close-in, low-altitude nuclear detonation as the price of a genuine last resort was how a program built with 1960s and 70s technology solved a problem modern guidance systems still take seriously. The mistake almost everyone makes is treating the fact that this system existed as proof it was ever meant to be the main event. There was, however, a limit the 10-second solution never solved, and it is worth being honest about it. The ABM Treaty had frozen Safeguard's entire interceptor inventory at 100 missiles. In 1974, the Soviet Union fielded the R-36M, the missile NATO called the SS-18, capable of carrying 8 to 10 independently targeted warheads on a single airframe. A defense built to answer one incoming warhead at a time was now facing missiles that arrived as 10 problems instead of one, and the treaty gave the American side no way to grow its interceptor count to match. Analysts call this a cost-exchange ratio, the price of a single warhead measured against the price of the interceptor built to stop it. And by the mid-1970s, that ratio was moving in exactly the wrong direction for the side playing defense. Nuclear fratricide had been the engineering problem Bell Labs actually solved. Multiplication was the one nobody solved, and it is the quieter, less dramatic reason Safeguard's entire approach was already running out of road even before Congress voted to end it. Even people who get this far usually assume the story ends the same way. Most retellings stop with the House Appropriations Committee vote on February 10, 1976, to shut the program down, formal deactivation following that April, and the image of the Michelson complex sitting empty in the North Dakota snow. A program that had cost $6 billion and run for about 6 months. That part is accurate, and it is also not the whole picture. The missile site radar, the system that would have actually guided every Sprint launch, was housed inside a 5-story concrete pyramid that alone cost close to $140 million to build, roughly $800 million today. After the shutdown, that pyramid and the Sprint launch sites around it were simply left standing, and for decades, nobody wanted them. A group of Hutterite farmers eventually bought the property in 2012. More recently, Cavalier County's Development Authority has been pitching the same pyramid, the one built to guide nuclear interceptors, as the shell for a data center, backed by a proposed $500 million investment. But one specific piece of the complex never got left behind at all. The perimeter acquisition radar, The other half of the detection system was reactivated the following year, in 1977, and has been running in some form ever since. Today it operates as part of Cavalier Space Force Station, under the United States Space Force, tracking objects in orbit as part of a mission descended directly from the job it was built for. The pyramid sat empty for 40 years, waiting to become something else. The radar next to it never stopped looking at the sky. So the popular version of this story, that the Army built a doomsday weapon and killed it within months out of embarrassment, is true and incomplete at the same time. What actually happened is closer to this. A program shed almost everything about itself, except the one piece nobody seriously questioned, and kept that piece running for nearly 50 years, quietly, without the fanfare or the controversy that surrounded everything else it once carried. Go back to October of 1975 for a moment. A nuclear missile switched on with the explicit job of detonating close enough to hurt the people it was defending. On the surface, still the single most reckless-sounding decision of the entire Cold War. Now hold that against the number you were told to remember at the start. 10 seconds. Under a minute, or over an hour. Nothing safe in between. Once you understand that window, sprint stops looking like recklessness and starts looking like the smallest, most reluctant, most tightly constrained answer that mid-century engineers could reach once the physics of their own weapons forced their hand. Add up the numbers this story actually rests on. 30 minutes of total flight time from launch to impact. 10 seconds of spacing that decided whether two interceptors could work together or destroy each other. 100 missiles, frozen in place by treaty, set against a Soviet warhead count that kept climbing for years after the treaty was signed. None of those numbers describe recklessness. They describe a program doing careful arithmetic against an opponent who kept quietly changing the equation. McNamara called Sentinel a light system back in 1967, before Sprint even had a finished design, meaning light enough not to provoke a Soviet buildup. It turned out to mean something far more literal than anyone in that announcement could have guessed. Light enough to avoid an arms race, light enough, in the end, to fit inside a 10-second window. It was never built to be used casually. It was built because 10 seconds is not a lot of time, and somebody had already done the math on what happens if you pretend it is. Somewhere in North Dakota tonight, a 5-story pyramid built to guide a nuclear interceptor sits waiting to be turned into a data center, and a few miles away, a radar dish that was never supposed to outlast the program it belonged to is still turning, still watching the same stretch of northern sky Sprint was built to defend.